I'm happy for everyone joining this talk. So this is a second talk in the webinar series. The first talk you can find a recording of in the link that Maria has provided. So this talk will be about cavity enhancement of modulation bandwidth in multi-section lasers. In fact, it will be two parts. The first part will be about cavity enhancement of modulation bandwidth in multi-section lasers. The second part will be about the program that I've developed called LaserMatrix, and we will also have a sort of a hands-on demonstration of LaserMatrix program. So let's start now here. So the outline of this talk is that I first, in fact, will talk about the bandwidth limitations of conventional directly modulated lasers. Then I will go into the three ways of cavity enhancement. It will be detuned loading, chirp intensity conversion, and photon-photon resonance. And then I will end with the conclusions and a demo. And also this introduction to LaserMatrix. So first of all, why DMLs? Well, you can either modulate the laser by changing the current to the laser, or you can modulate the laser by having an additional section of a laser called electroabsorption modulator or a modulator, where you can modulate the light. In that case, the light from the laser is constantly on, and then you shut it on and off with the modulator. They have different advantages. The direct modulated laser is so-called simpler to fabricate. It gives also higher output power, since a modulator always have a loss, and it also gives an inherent linear modulation. When you change the current, the output power of a laser changes approximately linearly. The externally modulated laser, it has lower chirp. Chirp means that the wavelength change when you change the intensity. In the external modulated laser, that problem is much less. It also has normally higher modulation bandwidth and also higher extinction ratio. That means that there is a larger difference between the zeros and the one. So in a directly modulated laser, maybe you can have the one symbols that are 4 times more bright than the 0 symbols, whereas in the external modulated laser, it can be more than 10 times, even 20 times more brighter ones than zeros. So this means that directly modulated lasers, it's mainly used in the datacom and short distance networks, because otherwise the chirp will become a problem. And of course, there are efforts to increase the bandwidth and extinction ratio then of DMLs to compete with the EMLs. So to understand the laser, I will not go through the laser theory, but this picture, in fact, quite well give an understanding of the laser. When you change the current to the laser quickly, the carrier density in the laser will increase. That will give chirp, because the chirp comes due to the change of the carriers. The increase of the carrier density will then give stimulated emission here, so and increase then the number of photons in the cavity. But then the number of photons will give increased stimulated recombination, which tries to suppress the carrier density by stimulated recombination. And this means that if you change the current slowly, in fact, the carrier density about threshold will hardly change. So if you change the current slowly, you will not change the frequency. But when you start to do it rapidly, this feedback loop then stops to work well, and then you get chirp. And apart from chirp, you also get distortion. This linear behavior doesn't work as well. So by having a large feedback gain here in this loop, you can make this loop work at higher bandwidths. And the feedback gain is given by how much, when you change the carrier density, how much the stimulated emission change. So it's mainly dependent on how much the gain change when you change the carrier density. That is called the differential gain. So if you have a large the GDN, that a large increase of a gain when you increase the carrier density, you can get a laser with high linearity, also high bandwidth, low chirp, low line width, and large feedback tolerance. Everything becomes better with larger differential gain. So that in a conventional laser, then that is what you try to do. You try to make a material with high differential gain, and that you can do with quantum wells, for instance, and so on. When you look how this laser transfer function looks like, then you have this three-pole behavior of a laser transfer function, whereas this term here, this parenthesis here, is this feedback loop I explained, and it works up to a certain resonance frequency where it has a resonance, and then it gives a decay of a modulation response. Then you have also electrical parasitics that gives another first order parasitic roll-off here. So this laser transfer function very well described a conventional semiconductor laser. The resonance frequency here, it increases approximately, the resonance frequency square increases approximately linearly with the current about threshold. And this then D factor here, it depends then on the differential gain, which is here represented by this little a here. That's the differential gain per per square meter, in fact. The D factor is determined by a material differential gain. The confinement factor, as you see here, that is also how well the carriers and photons overlap, and the active volume of a laser. So if you want to get a large resonance frequency, you want to have a large differential gain, a large confinement factor, and a small volume of your laser. Then there is another term here which gives the damping of a resonance frequency, and that can also limit the bandwidth. This damping factor, you want not to have neither too small nor too large. And it's given by this, physically, it's given also by the differential gain. If you have a large differential gain, this K factor here, how much the damping increases with the resonance frequency square, then decreases. But it's also given by the nonlinear gain here, the gain compression of your laser, and the photon lifetime here. So if you want to have a low damping, you should have a small photon lifetime, a small nonlinear gain, and a large differential gain. And this nonlinear gain is determined by spectral hole burning and carrier heating, and whereas the photon lifetime is determined by the mirror reflectivities and the losses inside the laser. Then finally you have a parasitic roll-off, and that is determined by the electrical parasitics of your laser. It could be contact capacitance and the series resistance, which gives an RC roll-off. It's also dependent on the driving impedance you have, and also on carrier transport effects. So in fact, the parasitic, the transport effects is important, and if you have quantum wells here in your laser, and you have the P side here of your laser here and N side of laser here. If you don't dope this SCH regions, the separate confinement heterostructure regions, then the carriers, both the electrons from this side and the holes from this side, they need to be transported by diffusion, and especially the hole, they diffuse quite slowly. And this means that you have a lot of holes and electrons here in this SH regions that gives a capacitance. So even if you have low contact capacitance of your device, this can increase the capacitance and reduce the bandwidth. A remedy of this is often to lightly dope the SH regions, so you also have a drift current here, so it's not only by diffusion that the carriers are transported into a quantum wells. The drawback with having doping in the SH region is that you increase the losses of your laser, the optical losses, because you have free carrier absorption. So when you want to measure the laser, you normally measure its modulation response. That's the transfer function of a laser in frequency domain. Then you use a network analyzer here, and you send out a small sinusoidal signal here to the laser and see how the laser then reacts to this sinusoidal signal. Then you have a detector and give back the sinusoidal signal to your network analyzer. And the network analyzer compares the received signal with the transmitted signal here and see how the amplitude and phase vary. Depends then on the frequency it sent out. So it sweeps its frequency. So it measures the transfer function of a laser and detector. So here is an example then of this transfer function, which we saw, the three-pole transfer function. And the dashed curves here are the fitted values to this formula, whereas the solid lines here are the measured values. And you see that if you have a well-behaved laser and you have calibrated it, this simple three-pole formula quite well describes how directly modulated laser works. So when you do this fitting, you extract the parameters here. You extract the damping factor, the resonance frequency, and the parasitic roll-off. It's only 3 fitting parameters here. And then you fit it for every bias. You measure the transfer function of your laser for different bias, and then you fit these parameters. When you have done that, you can plot these parameters, and then you remember that the resonance frequency square, it was proportional to the current approximately. Here I put the resonance frequency squared as an x-axis here, and the current here as a y-axis. And the reason is, if you use the resonance frequency squared as x-axis, you can better then get the linear behavior between the damping factor and also for the parasitic roll-off. So it's better to use the resonance frequency square than the optical power or current on this on the x-axis. Then when you have done this, you can extract different parameters. You can extract this D factor, which we talked about, and this D here. That is the slope of this line. You can also see where thermal effects makes the resonance frequency to saturate. That is the maximum resonance frequency you can get. Here you can extract the K factor in the same way, and also the damping at very low currents. And here you can extract the parasitic roll-off here. Normally this is quite constant, especially if it's contact parasitics. If it's transport parasitics, you will see more behavior with more variation with bias here. So by extracting these parameters then, you can sort of, for each individual laser, calculate 3 bandwidth limits. It's the thermal bandwidth limit that is caused by the saturation of a resonance frequency. It's thermal effects. Above a certain current, the intensity of a laser stops increasing, and also the bandwidth of a laser stops increasing due to that you heat up the laser. And then when you heat up the laser, both the transparency carrier density goes up and the differential gain goes down, and then you don't get improved bandwidth anymore, even if and also the photon density goes down. So this gives then a thermal limit. If you just know what is the maximum resonance frequency, you can calculate the 3D bandwidth of your laser. If it was only limited by thermal effects, then you can calculate that 3 dB bandwidth. Then instead, if you have perfect cooling of your laser, you can see what would the bandwidth be if you can improve the cooling. That would be the damping limit, and the damping limit then is given by the K factor here, how fast the damping increases with resonance frequency square. That will also give a maximum bandwidth of your device, a bandwidth which is higher normally than the thermal limit. But it's good then to see what is the potential of your device if you can improve the cooling of your and decrease thermal and electrical resistance of your device. Then the last limit is a parasitic limit, and that you also can calculate. You can calculate what would the bandwidth of a laser be if it was only limited by parasitical effects, and you didn't have any thermal effects and damping effects. And that parasitic limit is given by this expression. It's higher than the RC cutoff because you still have a resonance frequency that sort of helps to equalize the RC roll-off here, you see. So you can reach a higher bandwidth than the RC bandwidth here, but it has a limitation, and above a certain current, you see the bandwidth suddenly drops to this RC limited bandwidth. So this maximum bandwidth is given by the parasitic limit. So for each device you fabricate a measure, you can calculate these three limits. And then you can see which of these three limits is the most hampering your device the most, and then you can work with that to improve the bandwidth of your device. So if it's thermal effects, you should improve the cooling and decrease the thermal resistance. If it's parasitic effects, maybe you should dope a little bit more heavily the activator or improve the contact of your laser. If it's damping effects, you need to decrease maybe the photon lifetime by reducing the reflectivity of your device, the effective reflectivity of your device. So by calculating these limits and extracting them for an individual laser, you can see what is the most successful route to improve the bandwidth of that laser. If you do this, you can come to a bandwidth of around 25 gigahertz or something like that with a conventional laser. To go beyond 25 or maybe 30 gigahertz, it's very in indium phosphide material, it's difficult. So then we can say the recipe for result for a high-speed laser is to have a high modal differential gain to get a good D factor, a high photon density, and in order to get that, you need to have low heating and good cooling, and small electrical parasitics. That means, yeah, you should optimize your electrical contact and also see that the series resistance and carrier transport to your wells are optimized. If you want to go further than this, then you need to use laser cavity to enhance the modulation bandwidth. And I will go through three effects that helps to enhance the modulation bandwidth by using the optical cavity for this. It's detuned loading. It means that you use this wavelength selective reflectivity to speed up the laser response. I will go through it and explain it. Then it's chirp intensity conversion. In fact, the FM response of a laser has a higher bandwidth than the AM response. So by converting FM to AM within your laser, you can in fact improve the bandwidth somewhat. And the third one is photon-photon resonance. Then you use a weak side mode, a weak cavity resonance, to resonantly amplify one of the side bands of your modulation, and that becomes the sort of optical equalization of your modulation response, which also boosts the modulation bandwidth at high frequencies. So let's start with detuned loading. So detuned loading works like this. I told you that when you change the current in your laser, the carrier density here will change a little if you do it rapidly. Then you get chirp, which was the problem. However, you can utilize this because if you have a DBR laser, here is the active section and here is the Bragg reflector, then mirror reflectivity will look like this. It will be a high mirror reflectivity at the Bragg wavelength of this grating and lower reflectivity when you are at wavelengths deviating from this maximum reflectivity. And then you in fact can change the phase condition of your laser, so you force it to lace on the long wavelength side here. I mean, in order for a laser to lace, not only the amplitude condition needs fulfilled, it will be most easily fulfilled here. but also a phase condition needs to be fulfilled. And I have then you can make the laser lace on a long wavelength flank here by adjusting the phase condition. And when it does so, when you increase the current here, suddenly, not only you increase the gain in the active section, you also, when you increase the carrier density, the lasing mode here will shift towards shorter wavelengths. That means that mirror reflectivity will go up, the losses, optical losses go down. So it means that when you increase the carrier density here, not only you increase the gain, but you also reduce the optical losses. And that will give a more sort of higher effective differential gain. You change the gain minus the losses a lot if you are modulating on this flank here. So on this flank, you improve the bandwidth. On this flank, the bandwidth will be reduced because here you reduce the reflectivity when you increase the carrier density here. So it's not good to be on this flank. But on the long wavelength flank of a Bragg peak, then you get an increased relaxation frequency. And this is quite a strong effect. It can increase the bandwidth with 50 to 100%. So in addition, there is another more subtle change. There will be a small time delay between when you change the carrier density here and when the reflectivity changes. It's a very, very small, it's in the order of picoseconds. It's a very, very small time delay, or even fractions of a picosecond, but it will also reduce the damping. And that can also be beneficial since you get a more peaky resonance frequency. You don't want it to be too peaky, but this peakiness can then equalize capacitance, for instance, of your laser. So utilizing this, you can see here experimental results. So here we are located here on the short wavelength flank, then we get a low bandwidth. Here we are located on long wavelength flank, and we get a much enhanced bandwidth here, you see. It's in the DBR laser. Here we also see that since you increase the effective differential gain, then you also get much better spurious-free dynamic range if you have analog applications. I said the distortion gets lower if you have high differential gain, and here the spurious-free dynamic range then increases a lot if you are on the long wavelength flank here compared if you are undetuned or on the short wavelength flank. Also the chirp will reduce a lot, and this here is the spectrum during modulation, the spectral broadening, and the spectral broadening becomes much less if you are on the long wavelength flank than if you are on the short wavelength flank when you modulate. And this is because then the chirp factor of your laser, the structural chirp factor, will reduce. So when you change the intensity of a laser, the frequency will not change so much, and this is also due to the higher effective differential gain. So with this, we published, this is a very old paper in 1997, but then we reached, by utilizing this effect, we reached 30 gigahertz and 40 gigabit per second in DBR lasers, 1997. So, and that was at that time world record then. People had tried to reach 30 gigahertz by optimizing the quantum wells, but it was really this detuned loading that helped to go beyond that limit. We also saw, however, that you should not have too much detuned loading, because then I said that if there was the second effect reducing the damping, and if you have too much detuned loading, the laser starts to self-oscillate on the resonance frequency. So it starts self-pulsating at the resonance frequency, because the resonance frequency becomes totally undamped. So you need to design the laser to have not too high slope on the long wavelength side. It should be, optimized. Another thing that is improved is the reflection tolerance. In fact, this is a paper by my colleague Matsui, Yasuhiro Matsui, who unfortunately passed away in 2022. We designed this kind of very high-speed lasers, and we saw then that the reflection tolerance improves also. And the reason for this is that the reflection tolerance is critically depending on the alpha factor, that the chirp factor of your laser. So when you reduce the chirp factor of your laser, you also improve the reflection tolerance. So compared to an ordinary DP laser, where you need to have a reflection which is much less than 1% in order to not get excess noise and instabilities in the laser. In fact, the most detuned lasers, for instance, is DR lasers, there you could work without having an isolator because it could handle up to towards 10% or even more reflection before it started to started to behave chaotically. So this is also an important benefit of detuned loading. So that is what I wanted to talk about, detuned loading. Then the next effect is chirp to intensity conversion. And the chirp to intensity conversion is sort of similar to detuned loading, but you use the wavelength dependent transmission of a grating instead of a reflection. In fact, if you have a DBR laser like this with an active section here and a passive Bragg section here, you get higher bandwidth if you measure from the Bragg side than if you measure from the gain side here. So here you can see this difference. You see that from the Bragg side, you get higher bandwidth, but you also get lower slope efficiency and lower modulation efficiency. But together, you get much higher bandwidth due to this effect. So if you want to have a really high bandwidth, you should take your signal out from the Bragg side of your laser, and then you can have a HR coating here, high reflective coating on the gain side. To understand this, why it is like this, is because if you look at this is the AM response from the left section. From the right section, from the Bragg section, the AM response, it will not only be AM, it will also be dependent on the FM response, because when you change the frequency change of your device, then the transmission of your mirror will change. And so when it blue shifts, it will reduce, and when it red shifts, it will increase here, the intensity. And that will give them the FM response of a laser has larger bandwidth than the AM response. And if you add a little FM response to the AM response by this FM to AM conversion, you get this behavior that you get an effectively larger modulation bandwidth here. The drawback is also that due to the adiabatic chirp, that you get a little bit reduced slope efficiency here. So the contrast, the extinction ratio decreases a little bit. So that is what I wanted to say about FM to AM conversion. Now we come to maybe the most important effect. It's photon-photon resonance. And that is to use weak cavity resonances to optically equalize and boost the modulation at high frequencies. So when you modulate, here we have a spectrum, a spontaneous emission spectrum of your laser. The main peak here is the lasing mode that you have here. And then you have side modes. All these ripples here are side modes. When you modulate, you get extra spectral components. You get an upper sideband and a lower sideband here. When one of these sidebands enter cavity resonance here, like this sideband here enters this cavity resonance here, it will be optically resonantly amplified. And that means that the laser, this sideband will feel the laser like a resonant semiconductor optical amplifier, which improve the magnitude of this sideband, and hence it works like you can think of as an optical equalizer. So at high frequencies, when you have a sideband here, then it will be stronger than when it is here at lower frequencies. So this will give an extra resonance to your laser response, not only the carry photon resonance you normally have, but you will also get the resonance just because of this, that the sideband enters one of the side modes, and that is called the photon-photon resonance. So this, in fact, we saw already then when in 1997, we saw that in some of our devices, we could get even higher bandwidth than 30 gigahertz. We could get 31 gigahertz bandwidth. And we saw also that it was not possible then to fit the response to ordinary three-pole model at this high currents where this extra resonance occurred. And then we tried to understand what this was due, and we wrote that a possible explanation for the extra resonance peaks seen in this figure could be that one sideband of a modulated signal coincides with the side mode of a cavity and becomes resonantly amplified. And after that, in fact, all world records when it comes to bandwidth enhancement, or the bandwidth of DMLs, have been due to this photon-photon resonance enhancement. And the highest bandwidth it has been published by MCT. I will talk about that later in the talk when I talk about LaserMatrix. Right now, I will focus on what I did together with Yasuhiro Matsui at Finisar. We reached 55 gigahertz bandwidth and then 80 gigahertz bandwidth in our lasers. So I will talk about that now. So we looked at three different designs then to get this photon-photon resonance. First, the DBR laser, which I already talked about. We used two different coupling coefficients in order to try to not get the light to penetrate too deeply into the Bragg grating, but still having this improved slope that you get by a long Bragg grating. And then we had it was a semiconductor optical amplifier at the output to compensate for the losses in the Bragg grating. Then the most successful design, it was just a deeper laser where we had a passive section here and a low reflectivity of around 3% here. Then this external cavity then gave this side mode very close to the main mode that we wanted in order to get this photon-photon resonance. And then we also had another kind of DR laser where we have a corrugation both in the active section and in the Bragg section, which also gave this photon-photon resonance effect. And here you can see the modulation response of these. They are not very well calibrated, but you can see this extra resonance you have here, and maybe most clearly here. Unfortunately, they were not able, I should say, to measure higher than 67 gigahertz here. So you don't fully see the resonance here. But you see that you get extremely high bandwidth here, towards 80 gigahertz bandwidth of the DFB plus R laser here. And here we have this 70 or 80. This is one of the samples. It has around 70 gigahertz bandwidth. Here you see the bandwidth. Then for this sample, it has this resonance at slightly lower frequency. It's but it gives them 70 gigahertz, approximately 3 dB bandwidth. And this occurs very close where the laser mode jumps. So you need to be very close to the kinks here in the Li curve in order for this to happen. Either there are two mode jumps here, either at around 40 milliamp and another one at 75 milliamp here. And we could get highest modulation bandwidth and best results at this second kink here. So you see, you need to bias the laser very accurately. This means that this is also very sensitive to temperature changes and so on. So that means it's not right now as it is so commercially interesting, because you want, especially for DMLs, you want them to be temperature insensitive. In order to model this, it's possible to model with my LaserMatrix software, which we used for the design. And then you see a very similar behavior here, these kinks here. And just before the kinks, you see you reach very high bandwidth. And it's due both to photon-photon resonance, but also detuned loading. Here you have both, and also, in fact, FM to AM conversion. So we use all three effects here to get high bandwidth. And here you see that the model bandwidth can be above 80 gigahertz even. However, if you are biased at another point here, you don't have so high bandwidth. So if you're biased on the short wavelength flank of your reflectivity curve, then yeah, the bandwidth is much less. So here are some experiments we did. We published at OFC. It was made by Oscar Rossolins. He measured at T-sites. It is collaboration with T-sites, in fact, within the Twilight project, where we measured on this DML. And then we used Keysight's latest arbitrary waveform generator, and also this was in fact a prototype at that time, and then also their fastest digital sampling oscilloscope. Both have a sampling rate of 256 gigasamples per second, and then we had this laser here without optical amplification, then and 6 kilometer single mode fiber. We were able then to get these results, which is I will show here. So we could transmit 256 gigabaud on-off keying with this DML, and 145 gigabaud PAM4, that is 290 gigabits per second, and 160 gigabaud PAM6, which is close to 300 gigabits per second with this device. And I will also show here the eye diagrams of the 6 kilometer transmission. So here you see that the eye diagrams for on-off keying, for PAM, and PAM6. I want to stress that although we didn't have any optical amplification, we had post-equalization here with DFE. So there quite many taps were used to get a good response, because even if it's the laser handled to these high frequencies, the modulation response is not flat, and hence it gives intersymbol interference that we need then to correct by having digital processing afterwards. So that comes to the end of the first part of the presentation here. So here are the conclusions. The modulation bandwidth of conventional DMLs is limited by either thermal effects, damping effects, or parasitic effects. If you want to go further, you can use cavity enhancement, which significantly can increase the bandwidth of directly modulated lasers. You have 3 effects. Detuned loading can increase the relaxation frequency and reduce the relaxation damping. And it's based then on the reflective selectivity of the cavity. Too large detuned loading causes self-pulsation at the relaxation frequency. FM to AM conversion of transient chirp to Bragg facet increases the modulation bandwidth. If you have adiabatic chirp, you also get the decrease of extinction ratio at low frequencies. Together, it gives quite a large increase of the bandwidth also. And then you have a cavity resonance equalization, also called photon-photon resonance, that enhances response well above the relaxation frequency. It gives a second resonance to your modulation response. And also here you have to be careful. I've not shown it, but you can get self-pulsations at the beat frequency between the side mode and the main mode. That is also mode locking. It's really mode locking. You can get mode locking between the side mode and main mode if you have too much photon-photon resonance. And it's a challenge to achieve photon-photon resonance enhanced designs with good yield and control. As I showed, you need to be close to mode jump and bias the laser carefully there. So yes, it's not ready for commercial applications, I would say, even though it's possible. It's shown it's possible to get very high bandwidths. And in fact, there may be possibilities to make this more stable, and so you can utilize it, but you need different designs. So that was the end of the first talk. I suggest we take 15 minutes break now, and then I will talk about LaserMatrix, this my software then to simulate this kind of devices. So let's take 50 minutes break. You are welcome to ask questions now if you have. So anyone who has questions, please raise your hand, and I hope Maria will be able to let you in here and ask them directly. Hello? Yes, I have a question here. So Hans, Maria, could you let Hans?
Yes.
Richard, it's me, actually.
Oh, okay.
Maybe it might be worth if you could mention, taking on your last comment, how easy would it be to fabricate these lasers? How close are we to have these at hand?
It's not difficult to fabricate them. The problem is that you need to adjust them carefully in order for them to give this high bandwidth. And you need to adjust them individually, and then you need to have some sort of tuning or feedback circuit if you have temperature changes. So all this makes it expensive. So it's not the fabrication in itself which is difficult. It's to get good yield and good, to get them working well in a real system. When it comes to these new designs, I don't want to go into that because I work with several companies on this, so I will not go into which IDs can be used to make this more stable. But there may be possibilities to do this, and I cannot say how close that is possibly to be realized, but there are efforts at least in this direction.
Okay, Richard, thank you very much.
Yeah.
I'm asking this question because I think maybe it is in quite a few people's minds. How close could we be to having them at hand? Because it's obvious that they are fantastic tools. And also, by the way, thank you very much for the presentation. It was very clear, very, very highly appreciated.
Thank you very much. Thank you, Michael. So, yeah, and
it's Hans Keimer from Chalmers here. I actually have a question about slide 26, if you can go back there.
Yes. There we have,
Yeah, so if we look at these responses for the very high bias current, so like 100, 130, 150, we see this low response at the low frequencies. Can you explain what kind of physical effect this is caused by?
You mean here?
Yes, exactly.
Yes. It may be the here we are close to having two modes in the laser, and the two modes will have different bandwidth, and they can be out of phase or in phase. So this can be due to the side mode that is modulated, the spontaneous emission in the side mode that is modulated. This may also occur if when you modulate with a laser at low frequencies, the modulation efficiency will depend on the impedance of a laser, and the impedance of a laser at low frequencies can change also due to different effects. Here, however, I think since it's only seen at high bias, I think it's a spontaneous emission in the side mode that is modulated here and the out of phase with the main mode.
All right, thanks.
You're welcome.
Richard, we have a question from Daniel Mija.
Yes.
Daniel, if you want, you can raise your hand and I can send you a request to unmute. Otherwise, I can for sure read out aloud the question. So the question is, on which sort could these results and effects be applied to EMLs?
So EMLs, you mean the photon-photon resonance and so on. In EMLs, it's not so interesting. It's possible to have, instead of external modulated laser, which EML stands for, to have a modulator in the cavity. And then, in fact, you can utilize this effect also, that instead of modulating with carrier density, you should modulate the electroabsorption or phase of your EML, and that you can do very fast. And the benefit of that, compared to modulating the carrier density directly, is that you can get the fundamental modulation response quite high, and then you can get this photon-photon resonance to occur at, this photon-photon resonance occur normally at 30 or 40 or 50 gigahertz from, and it's very difficult to get the modes so close. If you have an external modulator, you have a longer device and you have larger bandwidth, so it's more easy to get this effect. It's not, well, not external modulator. If you have an intracavity modulator, you can get this effect more easily, of course. But then the benefits of the DML is lost a bit, because then you still have the same complexity of a fabrication as an EML, and then maybe so intracavity modulators here are probably not so interesting commercially. But it's possible to use an intracavity modulator and utilize this effect. But for pure EMLs, there is no use here. Then for a pure EML, you just want a laser that has large bandwidth. No, a laser that has large power. And then the bandwidth of a laser itself is not important. It's just the bandwidth of a modulator that is important. So, yeah. So that, I hope I was clear, even if it was not the best answer, pedagogical answer. So yeah, you have no use of this if you're working with DMLs, but if you have intracavity modulators in your laser, you can utilize this effect.
Thank you, Richard. I can see Daniel has written that he's covered by your answer. Thank you. And we have another question from Alexander. Most of the best DMLs are designed for O-band wavelength around 1300 nanometers. Do you know any successful examples of DML with photon-photon resonance or detuned loading at 1550 nanometer, or there are intrinsic limitations due to quantum well material?
No, in fact, this device here is 1550, so you can make it's approximately the same, 1550 or 1300. Of course, it's 1300 is more interesting for datacom and so on, because then you can get better thermal behavior of your laser with gallium arsenide, and also at 1300 you don't have dispersion. So for datacom, 1300 is better. You can go longer distance without dispersion compensation. 1550, you can use this effect equally well. And as you see, this device here is 1550, and many of these records here, you see here, the first 3 records here are for 1550. And I think you can reach even 55 or 100 gigahertz also at 1550 if you just design the laser well and utilizing this photon-photon resonance effect. So I don't think that is a fundamental difference.
Thank you, Richard. So far, I don't see any other questions coming up.
Okay. Then let's take 5 minutes break. So I will just get something to drink, and I come back, and then we continue with the next part of the webinar.
Perfect.
Yeah, thank you. Okay. So, do you hear me?
Yes, we can hear you, Richard.
Should we start?
Yes, of course.
Yeah. So this second part of this webinar will be about LaserMatrix. It's a simulation tool for cavity enhanced directly modulated lasers, but yeah, it's generally a tool for any laser. So I will, the outline will be, first I will say some general things about the LaserMatrix simulation tool. Then I will explain a little bit about spatial hole burning, which is can simulate, and the transfer matrix method. Then I will tell a few words about the model result theory for modulation noise, which is then used in LaserMatrix. And then I will have some simulation examples and comparison with the other theories and programs, for instance, VPI. And I will end with conclusions and acknowledgement, and after that we will have a demo, hands-on demo of LaserMatrix. And I want already to say that the LaserMatrix, an evaluation, everyone who wants an evaluation version of LaserMatrix, I can compile a personal evaluation version. And so you can just contact me via mail. I will give that mail at the end, and then you can get your own personal evaluation version. The difference from of the evaluation version with the full version is just that you will not be able to save your structures. You can calculate on any structure, you can do all simulations, but you will not be able to save them. So yeah, the features of LaserMatrix is that it works for any longitudinal laser design. You can use it for multi-section DFB lasers, DBR lasers, and multi-cavity lasers. It's a modular result model. It includes then this coherent multi-mode coupling that is responsible for photon-photon resonance. It includes the detuned loading effects, the FM to AM conversion effects, gain compression, spatial hole burning, and also thermal effects. You have a large signal model for pulse distortion and chirp, and you can do PRBS simulations and eye diagram. You have an analytical small signal model, which is very fast for modulation response and intensity and frequency noise. And you can also calculate correlation between intensity, frequency noise, and intensity noise from forward and back mirror and so on. Then there is a parameter extraction model, so you can extract parameters if you have a spontaneous emission spectrum for any laser, both DBR laser designs or deep lasers, and the laser, and it's quite fast and efficient. And then everything is implemented with a user-friendly graphical interface, so it's a very fast learning curve. I use it even for my students, so they can do, a lab on it. So here is how it looks like. So yeah, this was I started development of this in 1986, in fact. So it's written for an older generation of Apple computers. It's written for the 68,000 and PowerPC processors. This means that in order to run this today, you need an emulator. And this, fortunately, there is a free emulator, and this emulator is available for all kind of operating systems. So you can run it on Windows, Linux, Mac OS, modern Macs, Android phones and tablets, and iPhones and iPads also. So regardless what you have, I have it even on my mobile phone. You can run this program, and it doesn't take a lot of space. In fact, the program itself, it's small enough to you can put it in an old-fashioned diskette. So it's just a little bit more than 1 megabyte of memory for the program itself. The emulator, however, there you need more space. So you need a few hundred gigabytes of hard disk space, and a few, maybe 100 megabytes or something of internal memory. So then you can define different materials in LaserMatrix. You can have up to 9 different materials in your device, and each material, the material parameters are the normal material parameters you have in basic laser theory. So it's gain parameters. You can choose between linear gain or logarithmic gain. Linear gain is for bulk material. Logarithmic gain is for quantum wells. That where you put in the differential gain and transparency carrier density, and also max absorption carrier density if you have a logarithmic dependence. Then you have the gain compression, where you have epsilon, the nonlinear gain coefficient you put in, and then you have a linear, the recombination parameters here, both linear, bimolecular, and or shear recombination. Then you can select if a material should be active. That means that you can have stimulated emission in it. If it should be tuning, then you can just inject current to change refractive index and loss in the laser. Or if it should be passive, then it's you cannot inject any current. It's just a passive section with a certain refractive index and loss. And and then you have also the possibility every parameter here can also be thermally dependent, and each parameter you decide then how much, if you want a linear dependence thermally or exponential dependence thermally. So you can then for any parameter here make them thermally dependent. By default, the parameters that I made thermally dependent is effective index here, which increases then with temperature, the differential gain, which reduces with temperature, the transparency carrier density, which increases with temperature, and the shear recombination, which increases with temperature. So, and here you also put in then the electrical resistance and thermal resistance for a very simple thermal model, so you can get the temperature of this section. And different section can have different materials then of your laser, and it can also have different heat sink temperatures, so it's possible to adjust that separately. The most important routine in LaserMatrix is this versus that. That makes it possible to change any parameter, either material parameter or section parameter, and then calculate how the output of a laser will behave. So as output, you can either have a static steady-state characteristics like the threshold gain or the threshold current or the wavelength of laser or the output power of a laser, or you can have rate equation parameters. If you want to model your laser, you can calculate how rate equation parameters then depend on different input parameters. So you can get the photon number in your laser or carrier number, and then the stimulated gain rate, the loss rate, the output mirror loss rate, and spontaneous spontaneous rate, and also the spontaneous recombination rate, and so on. Also the Peterman factor and longitudinal confinement and reactive confinement. I will not go through that. Then you have a modulation. In the modulation menu, you can get AM response, FM response, photon response, carrier response. You can calculate the bandwidth as a function of any parameter, the relaxation frequency or the damping factor for any parameter. In fact, you can do relaxation damping for all resonances in your laser, both the carrier photon resonance and the photon-photon resonance. So you can also calculate this adiabatic chirp and transient chirp and the structure alpha parameter that I talked about. When it comes to noise, it's the same. You have AM noise, FM noise, photon noise. You can also calculate the spectrum here above threshold, taking into account the carrier fluctuations. Then you can calculate correlation between different noises, and then also relative intensity noise, of course, at low frequencies. So it's possible, for instance, to simulate squeezing, multi-mode squeezing with this model, and I think it's the only model that can do that. And then you, of course, the line width. You have different line width measures, and the effective alpha parameter of your laser, and the feedback tolerance, which I talked about, how much reflection tolerance you have. And you can do this then versus any other parameter. Then you have a distortion. You can calculate second and third order distortion of your laser if you have analog applications. And then the APGISA menu, it can be either then section parameters or it can be material parameters. So, and you can have then each of these things up to as a function of two parameters. For instance, here is the AM response as a function of modulation frequency and bias current in the section, and then you will get several curves, then one curve for each bias. Other feature is that you quickly can get information about the laser at the current bias point, what is the threshold current density, threshold current and output power, and the noise and the rate equation parameters at the present bias points. You can do transient response. You can have different kind of current pulses in. You can have PRBS. Or either on-off keying or 4-PAM signals into your laser large signal. You can also modulate gratings. So along length of a grating, you can change the chirp of a grating or loss or coupling coefficient of a grating. And this can also be used for, for instance, simulating fiber gratings for dispersion compensation and so on, this functionality. So it works even with passive devices. And then you have a possibility to calculate the reflection and transmission of any section or several sections in your laser. And you can look at the effective length of the section, and both the magnitude and phase of the reflection and so on. So then the numerical solution methods, the longitudinal dependence, it's done by dividing the laser into small segments where the propagation constant and coupling coefficient can be assumed constant. Then I use the transfer matrix method. I will go through it a little bit. So the steady-state solution uses this transfer matrix method for each mode and carrier rate equation for each segment. And then I use iteration using modified Newton's method until convergence. And it includes the temperature dependence of material parameters, as I said. The large signal modulation, it's a temporal integration of modal amplitudes and carrier density using fifth order Runge-Kutta method. And then I have the small AM and FM response, small signal, and also the noise. It's a multi-mode model resolved dynamic model, noise model, which I will go through a little bit. So let's talk about a little bit what the transfer matrix method is. So and which is used, for instance, to simulate spatial hole burning. First, I want to explain then what spatial hole burning is. If you have a DFB laser, an ordinary DFB laser without any phase shift, and you have anti-reflective coating on both the facets, this facet and this facet, then it will, in an ideal DFB laser, will in fact not laser at one wavelength, but it will laser 2 wavelengths on either side of the Bragg peak of these gratings. And the reason why it doesn't lace where the reflectivity of these gratings is highest is because of phase conditions is not fulfilled there. So it is forced to lace on one of these 2 modes here, or on both modes here, the short wavelength mode and long wavelength mode. In order to remedy this, one can put in a phase shift here in the middle, just a little bit phase slip here to make the central corrugation period a little bit longer. It can be done by electron beam lithography. And then the grating has a slip here. You see here we have a quarter of a wavelength shift here. And then you can force the laser to lace exactly at where we have a maximum reflectivity, that is lowest threshold gain, and you get a single mode laser. And that's very nice. However, if you don't design this very accurately, and I will show it then on the hands-on simulations, you get something called spatial hole burning. And it's because that here in the middle where we have a large reflectivity, also the photon will, you will have a peak of photons here in the middle of photon density, since the photon doesn't penetrate very well. And you see this peak here of intensity in the middle of a laser. And that means that here in the middle, you get a lot of stimulated recombination, which will deplete the carriers. That is the spatial hole, which is, we talk about in the spatial hole burning. So in the middle of laser, we have less carriers. And that means that in the middle of a laser, the refractive index will be higher, because where you have low carrier density, we have a higher refractive index. And this means that in the middle of a laser here, the light is going slower, and then it's not a quarter wavelength shift here anymore. It's longer than the quarter wave. It's more close to half a wavelength shift, and then you are back to the DSP behavior where you have not one mode but two modes lasing again. So yeah, and this is a problem. In order to remedy this, you need to have a correct coupling coefficient, which is not too large in the quarter wavelength shifted the laser. I will show this later in a hands-on demo of a LaserMatrix. So in order to solve this, then we need to divide the laser into small pieces where we can assume the carrier density to be constant. And each such piece can be then described with the transfer matrix. The transfer matrix is approximately the same as the scattering matrix. It's just that instead of having output waves on the left side and input waves on the right side, which we have in the scattering matrix, we have waves on the left side, both ingoing and outgoing here, and waves on the right side, on this side. And the benefit of that is that you easily can cascade then several sections by just multiplying the matrix of each section cascaded then. So in order to demonstrate how this works, we can take a fabric raw laser here with just two mirrors. Then you can describe this mirror with this transfer matrix, this transmission in the gain material with this matrix, and this left reflectivity here with this transfer matrix. And then if you multiply them together, you get the transfer matrix of entire laser, which is here then. And then you see that the boundary conditions is that in order to have lasing, we should not need any ingoing waves into the laser. We should get outgoing waves without ingoing waves. It means that U left and V right here should be zero. And if we put in that here, and we see in order to fulfill this, A11 here, this matrix element needs to be zero. Otherwise, we don't get zero here. But instead of solving Maxwell's equation for this laser, you can describe it with transfer matrices, and then you just need to solve here the zeros of this complex variable in order to get all the modes of your laser. Then you get the resonance condition, and it will be fulfilled for certain wavelengths and certain gains here of inside the material. What the transfer matrix method do is to, instead of using wave equation and boundary conditions, you use the transfer matrix methods, and then this problem reduces to find the zeros of a complex function of two real variables, the frequency and the gain. So, for instance, if you want to model spatial hole burning, then you divide the laser into small segments like this. So, and within each segment, you assume the carrier density to be approximately constant, and then you can model this then and calculate what will the resonance condition be when you have spatial hole burning here in this case. And then you need to iterate, because when you get then a mode solution here, which you get from the transfer matrix method, it will have a new intensity distribution, and this new intensity distribution will change the carrier density distribution you assumed from the beginning, and then you get the new intensity distribution and the new distribution of the refractive index and gain in your laser, and that will give new mode solutions. So you need to iterate this until you get convergence in order to have a self-consistent solution of both the intensity distribution and the carrier density distribution. And if you have several modes, you need to do this with all modes, so to say. So you calculate all modes for this carrier density distribution. In LaserMatrix, in the static model, I assume it will be single mode, and then I get the carrier density distribution. From that carrier density distribution, I calculate all the side modes. However, dynamically, I take into account how all side modes are added together and affect the carrier density together. So in the dynamical model, it's fully multi-mode model. I will talk then about this model result theory I use. It's not published, in fact, but it's sort of similar to another theory, other theories made. So by a model result, laser model, then I need to explain. Either you can use traveling wave model, so then you calculate in time domain, you see how the wave in the laser is going during a very small time, how it's proceeding, and then reflected and going back and so on. So it becomes a temporal-spatial problem where you in fact need to have this discretization both in time and space consistent. And this, for instance, VPI, very famous simulation software, is using this. It's quite numerically efficient if you want to calculate large signal response and so on. So it's a good model. I have then instead used a model result model. So I expand the field. I describe the field not as an instantaneous field, but I describe it as a sum of eigenmodes of a cavity. So the total field is a sum of eigenmodes of a cavity. And that separates the spatial problem from the temporal problem. And then I get sort of a rate equation model, how the modes couple with each other, and also how the modes couple with the carriers. So the benefits of this is that it gives a simple yet exact analytical equation. For large signal simulations, it's not more efficient. It's, I would say, probably the opposite. But for small signal calculations, it's beneficial. And also it's very beneficial to understand what's going on in the laser, because you can select just one mode and see how the laser works if you only take into account one mode, if you take into account two modes, and so on. And then you can separate multi-mode phenomena from single-mode phenomena. Also, I can take away spatial hole burning if I want, or include spatial hole burning, and so on. So I can separate different phenomena in order to understand what is going on in the laser. Whereas the traveling wave model more works like there you need to sort of do experiments. It's like you have a real laser and you need to do experiments on it in order to understand what is going on. And also this linearized and then model expanded model, you can also make an analytical model just using one mode or two modes, for instance, which is also beneficial here. So then when you expand the field, you should use eigenfunctions, which should be orthogonal. In the laser cavity, in fact, the eigenfunctions are not orthogonal in Hermitian sense. Instead, they are biorthogonal. So they are orthogonal if you multiply them with their time reversed copy, so to say. So they are orthogonal in another sense, but still, then you can show they normally form a complete system. Then you can decide if you want to use rigid modes or instantaneous modes. I will just say, so in LaserMatrix, you can choose between these two kind of modes. Rigid modes are the modes at threshold. They cannot, after that, you have fixed your eigenfunctions. So that means that a mode, if you have a single mode model, it cannot take into account chirp or how the intensity changes during modulation. To do that, you need many modes in the rigid mode model. The rigid modes are fixed. They are not time dependent. They are only dependent on the space set here. Whereas instantaneous mode, there even a single mode model can be time dependent. So instantaneous mode, in fact, you can say you expand the field at every time point in a new set of modes. And then you calculate how the old set of modes couple to the new set of modes at each time point. This sounds numerically much less efficient, and it's true for large signal calculations. Here you need to solve at each time point the Maxwell equation of the transfer matrix method using the transfer matrix method. However, you can show that this change when you know the solution from the previous time point. You just need to look at the differential change. So it's not so much more numerically difficult. However, for small signal analysis, this is much better because here you only need to here you can use fewer modes. If you have a single mode laser, even if it chirps, even if the intensity distribution varies with time, you can define you need only one mode to describe it. If you want to calculate on PPR, normally you only need 2 modes to describe it. So it's sort of in such way it's more analytically, it gives more easy to understand analytical formulas. I will not go through this in detail. I can just show you here what I mean. If you have instantaneous mode expansion and rigid mode expansion for a D-bar laser with photon-photon resonance, for instance, and the detuned loading, they will give, if you use just one single mode, they will give very different results. You see here, the instantaneous mode expansion gives the result you see here to the right, and the rigid mode expansion gives this if you just use one single mode. But if you add modes now, you will see here it's with 2 modes, and I can say that instantaneous mode expansion already has converged here. In order for the rigid mode expansion to converge, you need to add more modes here. You see, here there are much more modes contributing to the response than in this case, where only 2 modes are needed. But the total response becomes exactly the same when you go in the limit of many modes in the instantaneous mode expansion and rigid mode expansion. So the end result will be the same in both expansions, just that you need more modes to describe the field if you use rigid modes. Yes. So then I will give some simulation examples in comparison with other theories. So here I will use then a D-bar laser exhibiting photon-photon resonance. So it's a D-bar laser. It has also detuned loading. The laser mode is located here. You have a photon-photon resonance mode located here. This resonance you see here. And it also will take out the light from the Bragg section. So it has also FM to AM conversion I talked about. And it also shows self-pulsation mode locking at high bias. It's an interesting sort of simulation model. So then we can look at the spectrum of this laser. If I only, this is a spontaneous emission spectrum. If I only include one mode, I have just a Lorentzian. If I include 2 modes in my calculation, I have 2 peaks. Then I can just include more and more modes, and finally I get the full spectrum here. So this is how a modally resolved model works. In the LaserMatrix, I have also a linear model. This model resolved model takes into account the carrier fluctuations. You can see side bands due to a small relative intensity noise and so on in this model. So it takes into account what happens about threshold interaction between the photons and carriers. There are in literature simpler models that doesn't take into account the carrier fluctuations. They assume they take into account the carrier noise, but not the fluctuations due to interaction of photons and carriers. And such a model was made, for instance, by my colleagues, Eilert Berlind and Lars Gillner. And here you see their model. It's very fast. It's a black. Let's see, the red curve here is a linear model which they use, and you see the black curve is a nonlinear model here. But it's when I use only 22 modes. If I use more than 30 modes, you cannot see any difference between a linear and nonlinear model when you are at threshold, because then they exactly agree for most lasers. It's only for DF lasers with AR-coated front facet. Then the modally resolved model doesn't really converge well. You need more and more modes, exponentially more modes with lower reflectivity you have. If you have 1% reflectivity, it's good with 50 modes or something like that. But if you go below 0.1% reflectivity, then you need hundreds of modes to describe the spectrum in this modally resolved model. So that this model LaserMatrix about threshold, the nonlinear model, is not working well for these lasers with perfectly AR-coated front facets. Here you can see then how the spectrum evolves with bias current. It's the same laser, so we start at threshold, and you see the red curve here is then the Eilert Berlind and the Lars Gillner curve. Here I use more modes, and we get quite good agreement. Then if I increase the bias to 25 milliamp, we start to see features here. We see 2 sidebands here caused by the intensity noise at the relaxation frequency. So that gives upper and lower sideband. So the spacing between the carrier here, the laser carrier, and this sideband is the resonance frequency of the laser. We also see that we have a strong side mode here that interacts with the main mode, and by gain compression give a small contribution here, which is sort of a four-wave mixing contribution here, which is due to that the gain is modulated by these two, and that will modulate the laser mode and give a sideband here at the same frequency difference that is between this mode and this mode. At 50 milliamp, we see then the resonance frequency increases, and we see that it goes towards this side mode we have here. Here we have a cavity resonance, and you see the resonance frequency here is moving toward that. It increases with bias and goes closer and closer. Here we see that we have a carrier photon resonance here and a photon-photon resonance here, which is the side mode, and they are coming closer and closer to each other. Now they go into each other, and then in this laser, we in fact get self-pulsations if we increase the bias further. So then you get mode locking between the main mode and side mode in this case. But just before you get mode locking, when you have this situation, you get very large bandwidth here. So you resonantly amplify your modulation response at these frequencies. So we can look here at the relative intensity of noise. Here on the left side we have LaserMatrix. On the right side we have VPI component maker. At close to threshold there is quite large difference between the models, mainly because then VPI gives a lot of noise at low bias. But if we increase the current, we get very results that are very close. A difference here is that in LaserMatrix, the model is linearized. It doesn't take into account the wideband FM response. You get just two sidebands here. In reality, since you have a chirp in your laser or chirp parameter, you will have vessel formed sidebands at more frequencies here, and that is given here in the time model. You see you have a broader spectrum here around the main mode here. If we increase the bias further, we see this photon-photon resonance effect, and also here in the spectrum, and then we see how it goes into self-pulsation in both models here. Here you will see now the modulation response, how that evolves. At low currents, we have just a single carrier photon resonance. Then we increase the bias, and then we see something happening here, and that is at the frequency spacing of a side mode. We have a side mode at around 60 GHz here, which then enhances the modulation response at these frequencies. And when then the carrier photon resonance come closer to it, we get very large bandwidth, and then finally, when it coincides with it, we get self-pulsations in this case, which is of course not normally what you want. And then it's possible in LaserMatrix to see really what happens here. Why do we get the self-pulsations? So you can plot then the resonance frequency and the damping both for the carrier photon resonance here and the photon-photon resonance here. And then we see that when you increase the bias, the photon-photon resonance damping decreases and become below zero, and then you get mode locking self-pulsations. Here is then LaserMatrix again versus we compare with VPI. So this is exactly the same structure in both programs, and LaserMatrix are the colored curves, and VPI are the dashed curves, and you see you get perfect agreement despite these two programs work in completely different ways. VPI is a terminal wave model in time domain, whereas LaserMatrix then is modally resolved. So so you get perfect agreement even for complex structures that shows photon-photon resonance if you have exactly the same structure in both programs. And here is also the FM response with chirp. Here you see you get perfect agreement between the colored curves and the dashed VPI curves. So the result will be the same in VPI and the LaserMatrix. And these comparisons were done, in fact, together with VPI at VPI premises in Berlin. So we, in this way, we saw that both programs really calculate correctly, and we didn't change anything in our programs to get this agreement. So both are implemented correctly. So you can trust VPI, but you can also trust LaserMatrix. Here are also a simulation of self-pulsation, the mode locking large signal simulations in LaserMatrix and VPI, and again you see you get quite good agreement. So this then I want to show another feature of LaserMatrix. Here is the world record laser DML. It has 110 GHz bandwidth. It was made by NTT. Why they get very high bandwidth in this laser is because they use an indium phosphide membrane on a silicon carbide substrate. And silicon carbide is an excellent heat, the heat conductivity is excellent. So this thermal limit of a laser becomes much higher. And in addition, you have a good confinement here because you have a good large refractive index difference between the indium phosphide and the silicon carbide material here. And this combined makes the laser, even without optical feedback, to have a 3 dB bandwidth of close to 60 GHz. With optical feedback to get photon-photon resonance, they get beyond 100 GHz bandwidth here. So, of course, I was interested in exactly how this laser design worked. So what I did was a little bit of reverse engineering. I took the spectrum here. You see they have plotted the spectrum with feedback here in their paper. And then I digitized this spectrum. And then I made a structure similar to what they have written in the paper. And then I tried to extract the parameters of that structure. So when I put in it in the beginning, of course, I don't get the same spectrum, but I get approximately the same features here. And then I let the program iterate here to try to match all the mirror reflectivities here, the coupling coefficient, the difference in Bragg frequency between this has the passive reflector here, and also the Bragg frequency here. And so I try to adapt all these parameters to get the best fit possible. But it's numerically done by using both Powell's method and Levenberg-Marquardt method. And then it's possible then to get almost exact the same agreement as you see here. The red curve is then the calculated spectrum, and the black curve is the spectrum they published. And then I could extract all parameters. And without doing anything else, I just kept the normal standard material parameters for the laser. I then looked how the laser worked, and indeed I get photon-photon resonance here. I could reproduce the 100 gigabit per second on-off keying here, and the thermally also the behavior is similar like there. So it's quite this to do parameter extraction from measured spontaneous emission spectra is quite powerful way to see what you really have fabricated. And then I come to the conclusions here before the demo. So LaserMatrix is a simulation tool for longitudinal laser design of multi-section D3D bar and multi-cavity lasers. A modular result theory for the dynamic coherence coupling between modes has been developed and implemented in LaserMatrix. The model takes into account thermal effects, longitudinal spatial hole burning, detuned loading, and the coherent modal interaction responsible for photon-photon resonance, asymmetric gain compression, and mode locking. The model has been analytically linearized for fast calculation of intensity modulation response, green spectrum, FM noise spectrum, and optical spectrum above threshold. And the theory gives good agreement with time domain and traveling wave models and can be reduced to 2 modes for deriving simplified analytical formulas. And I want to acknowledge some co-workers here, especially Dr. Yasuhiro Matsui, which I worked for 14 years together with Finisar. It was really he. I thought, well, you know, when Apple changed to their Intel processor, I thought that would be the end of LaserMatrix. Then this emulator came, and he wanted to use it, and it's thanks to him really that I continue to develop this program. Matsui, Dr. Yasuhiro Matsui at Finisar, and now Coherent, sadly passed away unexpectedly November 1, 2022. Yeah, so I'm sorry about that, but I'm very grateful that I'm opportunity to know him and work with him, because he was a passionate experimentalist and also a laser designer. Then I want to thank other colleagues and so on for encouraging me, and also to you for their use of LaserMatrix. And I also want to acknowledge EU projects, especially then Twilight, which is also financing these webinars, Griffon, and the Swedish project from Vetenskapsrådet, who have funded some of the development of LaserMatrix. So here are some companies and university using LaserMatrix today. So many big companies like Apple, Broadcom, Tool Labs, and HP, and so on are using the program. And free demo, as I said, is possible to obtain. You get it will be a personal copy, just compiled for you personally, with your name hard-coded in it. And what is meant with the evaluation copy is it's fully functional, except the possibility to save the structure and to do parameter extraction. But if you're interested, just mail me at this mail address here, or Schatz@kth.se, and I will compile and send you this personal copy. So then we are ready for the demo, and maybe should we take a few minutes break before the demo? I see the time is already almost up, but maybe we can take 2 minutes or 3 minutes break, and then I continue with the demo after that.
Perfect, Richard. Thank you so much for your nice presentation.
Thank you.
We'll be back in a few minutes.
Yes, maybe if there are questions, I can take them during this break. So if you have any questions on what, otherwise many of your questions maybe will be answered during the demo, I think. Yeah.
Mm-hmm.
No questions, maybe. So.
Not right now, as far as I can see. So I'm going to just write your email address if somebody wants to contact you directly, also at the chat.
Yes.
I have one small question, Richard.
Yes.
LaserMatrix, could it be? How can you interface it with other tools for example, system simulations like VPI that you mentioned, or I don't know, maybe.
Yeah, but what you can do is you can save the time traces, for instance. It's not possible to directly run the program from another program, but of course you can export as text files all results and to do post-processing.
Okay, thank you.
Yeah. If you have VPI, you don't really need LaserMatrix, I would say. LaserMatrix is it's an alternative to VPI in a way. VPI can also calculate on these photon-photon resonances and everything. It's a very versatile program. But it's maybe LaserMatrix is more intuitive, much easier to use, and faster to design a laser than VPI. VPI is good to simulate when you have designed a laser, to simulate its performance in a system, for instance. So they complement each other in a way. LaserMatrix is just purely for the laser design, whereas VPI is more for the system design when you have finalized your laser design.
Maybe in LaserMatrix you can define better the material system that you want to use. I don't know, is there any?
No, in fact not. You have the same possibilities in VPI. I think at least you can do the same in VPI and define different material parameters for different sections and so on. The benefit is more the usability, the user interface of LaserMatrix. It's much easier to use for students and to quickly test. It's interactive in the design. So since it's quite fast, you can design and change parameters quickly in LaserMatrix. I will show it during the demo, and then you will see. You can compare it with VPI. Yeah, there is Giancarlo here from 35 Lab.
Yes.
Question.
Just give me a second, Giancarlo, to send you a request to unmute.
Can you hear me?
Yes, I hear you.
Okay, just a question about the grading geometry that you can implement in LaserMatrix. You mentioned the possibility to simulate chirp grading. At which extent would you have flexibility to define like arbitrary grading geometries in it?
In fact, there are two ways of doing it. Either to use the chirp grading function, then you are limited to certain functions, like you can have a sinusoidal variation, quadratic variation, or a polynomial variation of your grading, or exponential variation of grading, and you can do it in several sections. Otherwise, you can also have a complete possibility to define your grading from scratch, layer by layer, and then tell the program that repeat this layer stack this number of times. So then you create a substructure where you define your laser as one period of your laser in that. And then another way is then to have several such substructures with different parameters in. You can have up to 20 sections in your laser, and each section then can have different period in it. So there are different options. I will not be able to show that now, but if you are interested, just send a request and I will send you a demo, and then you can try yourself. Okay, should we start with the demo then?
Yes, I'm not sure if Giancarlo would like to ask something else because, okay, he has lowered hand. Okay, thank you.
Thank you. So then let's share another screen here. So I stop sharing this, and then I will share my emulator section instead. Okay, I hope you can see. I hope I can find my cursor also yet. So I hope you can see now the emulator screen. Maria, is it visible?
Yes, it is up.
Okay, so now I will demonstrate then LaserMatrix, how to use it. So first here, I will then open up the program. When I open up the program, I have different sections here. I can have a grading section, a homogeneous section, a phase section, or a substructure, as I talked about. This substructure structure can have any number of these sections repeated several times. So let's start then to make a simple Fabry-Provot laser. So I just enter here. I enter the material, the length, the current over threshold current density, the waveguide loss, and yes, this is if you want to change the index. Let's look at the material first. Here are the material parameters. Right now, I have different predefined materials. I have indium gallium arsenide phosphide here. Here is some tuning material. I have air. You can put in, define your own materials here and use them in the structure. So then it's possible to turn on temperature dependence here by just clicking here. Now I don't include temperature dependence to start with. Then also it's possible to change parameters of your laser. So you can change active layer geometry. You can put in the width, thickness, and confinement of your layer here. And you can also put in, say, program settings here. Then you can say if you want to use current or current density as input parameters, coupling coefficient or kappa L, and so on. And you can also say how many segments the laser should be divided into if you want to model, simulate, for instance, spatial hole burning. Now I divide it into 10 segments. So then let's see how such a laser works. We can just calculate first this versus that, and then it asks which wavelength range I want to calculate, and then here I can calculate then, for instance, the output power of this laser as a function of current density over threshold current density. So let's then go from below threshold to above threshold, so maybe 0.1 to 10 times threshold here, and see how then the current, how the output power looks like. And then you see here how the power increases above threshold, which is then 1 here. The power increases linearly here. Then we can see this instead in log scale. It's interesting. So I just change the scale here to log. And then we can see exactly what happens here at threshold, how you see the output power very rapidly increases here and then increases here. Then we can instead look, instead of having here current over current density, I will change this to current instead. So, and then we can see what happens with the laser if you increase to very high currents and calculate the same output power versus current. So I go up now to, I step the current from maybe 10 milliamp, which is below threshold, up to 600 milliamp. And nothing happens here because thermal effects are not included now. Then you see the current just increases. 600 milliamp in a 300 micrometer long laser is quite a lot. Of course, in reality, we would get the thermal roll off. And to demonstrate this, I turn on just the thermal dependence here, and I recalculate the same thing here, and then maybe I recalculate this, and then I change here just the color, so I put it completely red, and then, oh, yeah, then I get this curve instead. I should have plotted in the same graph, but you see, now you get the maximum power here, and after that, the laser decreases the power. You have a thermal roll off here, and of course in this region the laser can even burn and die directly, but this shows just how to use the thermal model. It's just to turn it on, and then you include thermal dependence in your simulations. The problem with the Fabry-Poro laser, it's spectrum. So if you look at the spectrum here, then the spectrum of this laser looks like this. So it has many modes here. It doesn't lace on one wavelength only. It laces on many wavelengths here. All wavelengths where the cavity is an infinite number of half wavelengths long, it will lace up because the phase condition will be fulfilled. And the amplitude condition is the same for all modes. So you have no mode of selectivity at all, which makes the Fabry-Poro parallel laser not possible to use for fiber optical communication, for instance, because different modes will travel with different speed in the fiber, and then you could not go a very long distance in an optical fiber. So in order to remedy this, normally use a deep laser. So then we can create a deep laser instead, having a grating here, and then it has a certain Bragg wavelength, and yeah, I put in here, and then we can also put here reflected power to 0, so we get a perfect deep laser. I will also bias it close to a threshold. I want to see what is the threshold of this laser. So the threshold is at 20 milliamps, so 21 milliamps. I put it at 21 milliamps, and then we can see how the spectrum looks for a perfect deep laser. So then we look at the spectrum here, and we see it lasers on 2 wavelengths here. And that is what I said, it's because the phase condition is not fulfilled. We can look, in order to understand this, we can divide this laser into 2 parts and look from the middle. So I will just copy here and divide it into 2 parts. And then we can look how will the reflectivity of these 2 gratings look like. So then I look the reflectivity of one of these grating, right one here, and I look at the S11 here, which is the reflectivity. And then also I ask the program to, oh no, I should S11, and to show the modes then on this reflectivity curve. And then you see, yes, now let's see. Sorry, I was not at threshold here. I should put it 21 milliamp. I need to calculate the threshold here again. It's the data for this laser. So the threshold is 23 milliamps, so I should have 11.5 in each. Otherwise, you get spatial hole burning, and then you don't see what I wanted to show. So here again, we can look at the spectrum first. So we see this, that it still has 2 modes just. You see, it has 2 modes here. And to understand that, we can look at the reflectivity spectrum then of this. So I look with reflectivity here, and then you will see that, yeah. You see that the laser either lasers on this mode or on both modes. So you see, we have not a good modal selection here. We have a bi-mode laser. In order to improve this, you can put a phase shift in the middle here. And I will put that phase shift here in the middle. And then we can see what is the optimal phase shift. I will now put the laser back to threshold. So just, we're not changing the threshold by doing the simulation. I bias it exactly at threshold. And then we can see how large should the phase shift be in order to improve the side mode suppression ratio here, or the gain margin of a laser. So then we can calculate here. Then we can calculate the threshold gain of the different modes, and then see where we have the largest gain margin. So yeah, and then I should do it versus phase shift here. So I take this versus that. Threshold gain versus phase shift. Then I mark here this phase shift we want to change, and then we can just calculate here and see which phase shift is optimal. And then you see here we have 0 phase shift. Then we have these 2 degenerate modes. They will both days. If we put in 90 degrees phase shift, which is quarter wavelength, well, then we have a really nice gain margin here. So then I put in the quarter wavelength shift here, 90 degrees. And then I look at the spectrum. Yeah. And then I have a very nice single mode laser here. And then also we can look then how it's lasing compared to the reflectivity curve now. The same picture we had before. And then we see now it lasers exactly at the peak of a reflectivity curve here. So now we have a phase shifted deep laser. And this works quite well, but if you increase the current density now here to 3 times threshold, for instance, and we calculate spectrum again. Then we see we are back almost to a DFB laser here. We have two modes again that are competing, and we have not a good gain margin anymore. And the reason for this is the dense spatial hole burning. So inside the laser, so if you look at the intensity distribution in the laser, as I said, you have a very peak intensity distribution in the middle of the laser here. It will give then a carrier density distribution, which have a dip here in the middle. And where the carrier density is low here, the refractive index, if you look at the refractive index distribution, it will be higher here. The yellow-blue curve here is the grating itself, but you see the average refractive index here in the middle is higher, and that means that the light is going slow here, and this phase shift, the accumulated phase shift here, will not be 90 degrees, but maybe 180 degrees, and then you are back to ordinary DFB laser, without any phase shift. In order then we can see what should the coupling coefficient be here in order to get the best gain margin at 3 times threshold here. Then we can check if you reduce the coupling coefficient, is it possible to get a better gain margin at 3 times threshold? So then we calculate this versus that. I change the coupling kappa L in these two sections, and then I look at the gain margin. So yeah, and then we can see here, then I change the coupling coefficient to something lower. So I go 1.5 per section to 0.34 per section or something like that. And then we see here where we get the larger gain margin. And then you see here that we have a very low gain margin. It was almost multi-mode here. But if you have a here, around here, we have a large gain margin in between the main mode and the side modes. So here somewhere you have a nice behavior. It's 0.63 in each of these two sections. The total kappa L of around 1.25. So we can put 0.63 here and 0.63 here. And then we can calculate then the spectrum again, and we will get a nice spectrum even at 3 times threshold. So then we can calculate the modulation response of this. Now this laser works quite well. Then I change again here to current in order to have current instead here. So then I increase then the current here and look how the modulation response of this device will look like. So I take here, I go to the modulation menu here and calculate the modulation response versus the current in these two sections. And then I can include several modes. It's a single mode laser, so it will not change anything. And then I think it will not be so high, so I go up to 30 gigahertz, and then I change the current from 30, which is around threshold, up to 100 milliamp. And then I click on return here, and then then I went from 20 up apparently, which is below threshold. I will go again and go from 30 milliamp here. And then you see how the modulation response then depends on the bias here of the laser, the total bias of a laser. And you see, the modulation bandwidth is not so good here, but yeah, it depends on that this laser is very long. It's much too long to be a high-speed laser. Another way of making a laser single mode is to use a D-bar laser, and I will now make a new laser here. I will take section here, make a shorter section then to make it better high speed, and I will bias it maybe at 90 milliamp here, and then I put on a reflector here instead, which is a Bragg section, but of a tuning material. So I change material here, And then I put, I can use a 300 micrometer section here. Upper end of 1 is good. Just the false values. And then I put on an AR coating here. Then you remember the fabrication device here had many modes. However, this grating here will select only one mode. We can look at the reflectivity of this grating. Yes, so I can matrix element. So we can look the reflectivity S22 of this grating and then look where the modes are. And then we will see here. So we see we have a one mode exactly then lasing where we have the reflectivity peak of this. The other modes are much suppressed here. So we get a nice single mode spectrum here. You can look at the spectrum. So here is the spectrum of this DBR laser. So then we can calculate the modulation response of this. Versus that. Then we take the modulation response as a function of bias in the active section here first, and then I can include several modes just in case we have some PPR. And then we can go from 20 to 90 milliamp, for instance, here. Look at the modulation response. So here we see then 20, 30, 45, 60, 70, 80, 90. And you see here the modulation bandwidth is better. We can see what is the modulation bandwidth here at 90 milliamp. It's 16.4 gigahertz, not extremely large. But now we will try to enhance this bandwidth by using the tuned loading. So I will replot this as dashed curve so we can compare them with the curves we get when we have good detuned loading. So I will just replot this and use dashed curves instead. So remember these curves. So now it's just so we have these curves. Then we should see what bias should we have then. How should we then detune load this laser? Well, this laser, a DBR laser, has a benefit. You can tune also the current in the passive section here. In that way, you can tune the wavelength. And I will show that first, how the wavelength is tuned in this laser by injecting current in the bright section. So then I inject current instead here, and I plot the wavelength. So here we have wavelength versus current in the bright section, and I don't need this. So, and I do it for 10 modes maybe. And 0 to 100 milliamp in the passive section then. And then you see how here how I will replot this so we see it. So here you see then how the lasers start here at the long wavelength. When we increase the current into the passive section, it jumps from this mode to this mode to this mode and to this mode. When this mode jump occur, during this mode jumps, you will detune the laser. So here it will lace on the short wavelength side, and then it goes to the long wavelength side, then it jumps to the short wavelength side, go to the long wavelength side. And then on the long wavelength side here, you get good detuned loading, which we want to have for high speed performance. So we can look at how does the bandwidth change when you then change the current in your passive section. So we keep the current constant in the active section to 90 milliamp here, and just see how the bandwidth will change when we change current in the passive section. So then I calculate here. I go and put in here the bandwidth, dB bandwidth versus current in the passive section, and bandwidth for the active section then, and then we just calculate here. I go again to 100 milliamp. It will take a little bit time since I have multi-mode calculation. So now it calculates the bandwidth for each current in the passive section, a constant current in the active section. And then you see the modulation bandwidth here. When the laser is lasing just before the mode jumps, you get high modulation bandwidth if you compare these two curves. Yeah. So for instance, here we have a very nice modulation bandwidth here. So we can put in maybe 26 milliamp in the passive section, and then we should have 25 gigahertz bandwidth instead. So I will put in 26 milliamp here in the passive section. And then we can calculate, just check that the bandwidth then becomes, then we see we have 25 gigahertz bandwidth here. Then we can calculate now in the same graph as we did before how the bandwidth depends on the current in the active section. So I will keep them 26 milliamp here to keep the detuned loading, and then change the current in the active section here. So that I do. So then I take the modulation response, and then I change the current in the active section here, and AM response for that section, and then I will plot in the old graph, but now I will not use dashed curve, so I use solid curves instead, and then we can plot it, and we can see how you can increase the bandwidth here. So you see the maximum bandwidth have increased from 15 gigahertz up to 25 gigahertz or something like that. So this is how you can use LaserMatrix, and that's what I think. Then we can test how does this laser work. Maybe you can use it for 20 gigabaud transmission or something like that. So let's see how this will work then. So I will first, in order to speed up things, I will neglect spatial hole burning because it's not important in the DBR laser. And then I will calculate the transient response here. And then I will put on the PRBS signal. So here we have PRBS signal. I will also only calculate with one mode since we don't have any photon-photon resonance effect here. And then we can take 50 picosecond here to get 20 gigabaud, and then we modulate maybe between 60 milliamp and 120 milliamp to get it's around 90 milliamp, 30 milliamp up and down. So let's see now how the eye diagram look like. Select which I need to say I should modulate this section. Yes. So I should not have this in. I should not change current. I should just have modulation. No, I will just then close the windows here. Close all the windows. So, and yes, and then now it will calculate the eye diagram of this. So if you have many modes and also include spatial hole burning, it can take some time to do this calculation, especially if you want to calculate many bits. But here you now see the eye diagram of this laser, and you see it works quite well at 20 gigabaud, probably also at 30 gigabaud. It would work well. And that is the end of this simulation. If you don't have any other devices you want to have simulated. So it ends also this webinar. So any questions?
Thank you very much, Richard, for taking us through the demo. It really looks like you can immediately see any change that you apply to the laser, and you can understand basically what kind of effect you are tuning.
Yes, exactly. That's the benefit of this LaserMatrix compared to VPI, for instance, where it's much more difficult to change parameters, and here you have everything integrated, plotting routines and everything easily integrated. You can do similar things with VPI, but it's a little bit less easy to use.
Indeed.
So I don't know if we have any listeners still with us, but if there are any questions, you are welcome to ask now. Otherwise, I guess this will be recorded and put up on the Twilight site. You can look at it later. And as I said, everyone who wants a copy of the program is welcome. Evaluation copy of the program is welcome to contact me on my email. No questions?
I see no questions at this point.
Yes. May I ask how many listeners are there still? Maybe we're quite, it took longer than I expected. I think many have gone to lunch now. But yeah.
Well, I think a few people left like at 12 o'clock.
Yes.
Still here like 19 people.
Okay, that's very. I want to thank you all for listening to this. And as I said, if you want to, you are just contact me, and I will compile an evaluation version for you. So thank you also, Maria, for this webinar. I'm sorry that this became a bit too long, but yeah, it was. I wanted to show also this demo.
Richard, thank you very much. Actually, it was very, very nice, and maybe people can contact you if they have any questions as well, besides obtaining a copy of the program.
Thank you very much, and thank you, everyone who listened. Thank you, Erkil. So yeah, so everyone is of course welcome to contact me. Also, if you have questions about DMLs or want help with DMLs, I'm also available. So thank you very much. So that, I guess, is the end of this webinar.
Thank you, Richard.
Yes, Richard. Thank you.
Thank you.